in halogen alkanes. Many types of isomerism undergone by alkyl halides are chain and position isomerism. Chain isomerism, this arises due to arrangement of carbon atoms in different chains. Example, C5H11Cl, CH3CH2CH2CH2CH2Cl, CH3CH2CH, CH3CH2Cl, 1-chloropentane, 1-chloro, 2-methylbutane. We have position isomerism. This arises due to the different positions taken by the halogen atom on the same carbon chain. 1-bromo, 2-methylpropane, 2-bromo, 2-methylpropane. Here, isomerism is the existence of molecules which have the same molecular formula but different arrangement of atoms in a molecule. The two types of isomerism we have here, chain isomerism and position isomerism, they are the main types of isomerism we have in halogen alkanes. For chain isomerism, these molecules have the same molecular formula, C5H11Cl. But the way these atoms are connected is different. But very specifically, the parent chains of the molecules are different, which means that the skeletal structure of the two molecules are different. Here the parent chain in the first molecule is formed by 5 carbons. That's why we have a pentane. While the parent chain in the second molecule is formed by only 4 atoms, which is butane. It means that the carbon connectivity in these two molecules is different. The second type of isomerism is position isomerism. Here, the molecules have the same molecular formula, and the only difference is the position of halogen within the skeletal structure or the carbon chain. When you look at the first molecule, the parent chain is composed by 3 carbons, and the halogen is attached on the first carbon. The second molecule, the parent chain is composed by 3 carbons, but the halogen is on the second carbon, while here is on the first carbon. When you look at their names, you will see that the only difference will be in the position of the bromo halogen. Look at here. 1, bromo 2-methylpropane, 2, bromo 2-methylpropane. So the only difference is between 1 and 2, and the rest of names are the same. That is to confirm that these molecules are different only in the position of the halogen bromine. So here is an activity for you. In your prep time, find the position isomers of this molecule, C3H7I. Give all possible structures of CFCs whose molecular formula is C2H2F2Cl2. Give all possible chain and position isomers of C6H10Clbr. For it to help you, every structure you find, try to name it. This will help you to identify which is the main difference between one structure and another. Physical properties of halogen alkanes. The very first few terms of alkyl halides are gases at room temperature. This is due to the weak random dispersion forces we have in short molecules of alkyl halides. We all know that the alkyl halides and other molecules have electrons, but as the number of electrons increases, the strength of random dispersion forces increase. So the very first terms means short molecules of alkyl halides mean that few electrons, weak random dispersion forces. But as the carbon chain increases, the random dispersion forces will become more strong and the molecules will become liquids and others become solids. The boiling and the melting points of alkyl halides are high compared to the corresponding hydrocarbons due to the intermolecular forces that increases because of high electronegativity of halogens, which induce the pores. But closely, this also takes place as molecular weight increases in the same series. To explain this, the alkyl halides have higher boiling and melting points than the corresponding hydrocarbons. Both hydrocarbons and alkyl halides have random dispersion forces as intermolecular forces. But in alkyl halide, we have another type of intermolecular force, which is called dipole-dipole interaction. That is to mean the alkyl halides have both random dispersion force and dipole-dipole interactions as intermolecular forces, while hydrocarbons have only random dispersion forces. And these are the weakest intermolecular forces we have. So that's the reason why the alkyl halides will have higher boiling point and melting point than the hydrocarbons, which have the same number of carbon atoms. But if we try to compare the boiling point of alkyl halides among themselves, but which have different chain lengths, you will see that as the carbon chain increases, the random dispersion forces will increase and the boiling point will be increasing. That's why the longer molecules of alkyl halides, they have higher boiling point than shorter ones. We have another example. Isomerism, bromomethane, chloromethane, and fluoromethane. These are alkyl halides which have the same number of carbons, the same number of hydrogens, and the same number of halogens, but the halogens are different. If someone asks you to order them according to the increasing boiling points, will you be able to do it? Will you be able to explain the trend? Let's try it. So, the boiling point of fluoromethane is lower than the boiling point than chloromethane, lower than the boiling point of bromomethane, lower than the boiling point of iodomethane. How can you explain this? These alkyl halides, they all have dipole-dipole interactions and random dispersion forces. The dipole-dipole interactions depend on the polarities of the bonds, while the random dispersion forces will depend on the number of electrons in the molecules. The differences in electronegativity of the halogens in the molecule are very close compared to the differences in the mass of these halogens, which means that iodomethane is much bigger than bromomethane, much bigger than chloromethane, much bigger than fluoromethane. And this gives the molecule the highest boiling point because it has the strongest intermolecular forces, random dispersion forces, compared to bromomethane, compared to chloromethane, compared to fluoromethane. That's the reason why fluoromethane is the one with the lowest boiling point, and iodomethane is the one which has the highest boiling point. The alkyl halides have characteristic order, and this is due to the halogens they contain. The relative density of alkyl halides is greater than 1, what is quite different to hydrocarbons. As you remember, the hydrocarbons, they have density which is less than 1, which means that they are less dense than water. But the alkyl halides, as you can see, their density is greater than the one of water, which means that they are more denser than hydrocarbons. To explain this, you can use the intermolecular forces as we explained it in the previous properties. This is to say, the alkyl halides, they have stronger intermolecular forces than the corresponding hydrocarbons. So this is the end of our lesson today, and the next lesson will be about the chemical properties of alkyl halides. I think you have enjoyed the lesson and you have got something from the explanations. Thank you so much. See you next